I welcome you to the presentation of this lecture on FET biasing. FET meaning field effect transistors. So, in some previous lectures we were talking about bipolar junction transistors, which are BJTs. In this presentation, we'll be looking at the biasing of field effect transistors. So, field effect transistors, for this one, my concentration is specifically biasing, not really what they are. So by definition, a field effect transistor is basically a transistor in which most current is carried along the channel whose effective resistance can be controlled by transverse electric field. So a FET or a field effect transistor looks something like this. There's three terminals. There's the terminal which we are calling the drain, the terminal we are calling the gate, and the terminal we are calling the source. So this is a field effect transistor. So in the biasing for this presentation, we'll start with the first one, which is the fixed bias configuration. So in the fixed biasing configuration, the circuit looks like this. So it has the excitation there, which is VDD. This is the voltage exciting that, and there is the voltage again exciting this, which is VGG. So VGG is connected to the gate, VDD is connected on the drain. Then there is a resistor on the drain, which we are calling RD, and the current flowing through the drain is ID. Then we've got the resistor connected on the gate, which is RG. The current flowing through there is IG as well. Then there's a voltage between the gate and the source. That voltage we are calling it VGS. And there's a voltage between the drain and the source, which is VDS. So a fixed bias configuration circuit will look something like this. So let's look at the analysis. So when you analyze in such a circuit, we'll split this circuit into two parts. We can split it where you get excitation from VGG, it goes through VGS, and then it goes to the ground as our first one. And the second one is we are getting excitation from VDD, it's passing through there, then it goes to the ground like that. So we'll start with this one, from VGG going there, you have that. So if you're analyzing using this one, in our analysis, RG is approximated to be 0 because it's very small. So the input there doesn't really matter. So a circuit will look something like that, where we are approximating RG to be 0, like there is no resistor there. So the circuit will appear like that. If it appears like that, then we can have the equation, which is this one, because we are saying RG is 0. So if RG is 0, we know that the voltage here and the voltage there, when they are added, they go to the ground giving a 0, which is this one. VGG plus VGS is going to give us a 0. That's the first equation. And then we can formulate another equation using these roots. Okay, so we can have another one from the exciter there, which is VDD. It passes through RD, which is the drain resistor, and then it goes to the ground like that. So with this, we are having that as our equation. VDD to have a voltage drop there, which is ID RD, and there is a voltage drop there, which we are calling VDS. So these are the two equations we are using, and the most important one is this one, the drain current. Drain current is basically IDSS 1 minus VGS over VP squared. So this VP and IDS, these are constants. When they give you a circuit, these will be provided for you. So let's look at an example in the next. So the question is saying, determine the following for the network shown below. They want us to find VGS, which is this one. We calculate ID, which is the current passing through the drain. VDS, which is the voltage between the drain and the source. VD, the voltage at the drain. VG, the voltage at the gate. And VS, the voltage at the source. So with that said, we start our analysis. I've started with this one. So with this, I said this can change where RG is 0. The circuit will look like that. From that, we can formulate the following equation. Since we're saying RG is 0, therefore VGG plus VGS, this is supposed to give us a 0, which is that one there. And then we know VGG has been given in the question there is 2 volts. So making VGS the subject of the formula, we are going to have VGS as negative 2 volts. That's the first one. Then we go to ID. ID comes from the previous equation I showed you, which is this one. Here, VGS, we just from calculating VP. VP has been given in the question there is negative 8. IDSS, it's been given, it's 10 milliamps. So if you substitute those, you realize that IDS, which is 10 milliamps, is basically the same as 0.01 amps. And then these voltages, they are the ones given there. If you do your substitutions there and evaluate ID, you realize that ID is going to give us that. We come to VDS. VDS, It's coming from this analysis. So if you analyze your circuit from there, you're going to have this. This was producing an equation, which is this one, where VDD has a voltage drop there and there. You're going to have that. If you substitute the missing terms there, VDD 16, ID times RD, these parameters we have, when you put them in there and you make VDS the subject, we are producing VDS as 4.75 volts. And then we have D, which is saying we find VD. VD is basically the difference between VDS is the difference between VD and VS, making VS, as we can see from a fixed bias configuration, it's grounded, so there's a zero voltage. So our VS here is 0. So if our VS is 0, then VDS and VD are the same. Therefore, VD will basically be the same as VDS. Then we come to VG. VG can come from VGS. We know that VGS is the difference between VG and VS. S is 0, therefore VG is also the same as VGS. So VG will also be that. And then we come to the last one, which is saying VS. VS is the voltage on the source. Since it's grounded, the voltage on the source is basically 0. So this is a presentation of the fixed bias configuration for the FET transistors. Thanks for watching.